Okay, so a couple slides ago we had this Fick's second law, and so we'll look at that now. And so hopefully we're now seeing that our second derivative for the concentration gradient with respect to position is reflected in the curvature in these gradients, in these concentration gradients, okay? So we see that idea very clearly now. And we see the idea that the concentration change throughout position x, if x is going from equals 0 to x equals some larger value, is also time dependent. We've touched on that. So this equation is a complex one to solve, and some partial derivative strategies are needed, and it's something past the scope of this course. But we're going to apply one of the solutions there where some boundary conditions, some assumptions have been made. So some of those conditions are listed here. Okay, so we'll go through them carefully and relate back to our zinc on copper idea. So the first idea is that we're going to assume the solid, the slab, the penny, is a semi-infinite solid with a constant surface concentration of the diffusion species. Okay, so that was the zinc layer on that copper, and that the copper is semi-infinite in thickness. Okay, so it goes very, very far relative to the amount of zinc that we are studying. Okay. Next, so right before any atoms have diffused into the copper, so this is T equals 0 by definition, any atoms are not in the sample, and we know that the concentration of the zinc at the surface is C0. Okay, so we also mentioned the idea that if the copper penny happened to already be processed to have a little bit of zinc, that this is going to give us that initial C0 value. Okay, so this was the sort of baseline value here that we see in our graph. Okay. Next, at position x equals 0, this might be the topmost surface of our penny. This is the beginning of the semi-infinite solid for us, okay? So it's the beginning of that surface slab that we're studying. Okay, so in this case, this is the top surface of the penny. It is where the copper meets the zinc, okay? So it's not the top of the zinc layer, but it's where the copper meets the zinc. Okay. And as we know, as we move deeper into the penny, we're going to, by definition, move from x equals 0 to more positive values. Okay, so as we go down from the top surface of the copper, where it meets zinc, x equals 0, deeper into the penny, we're getting positive values for x. Okay, we define T0. That's right when we start to get atoms moving in. That's when we start our stopwatch. Next thought here is that right when that starts to happen, the concentration of diffusion species is equal to C0 for all values of x. So let's unpack that. What does that mean? That means that just before atoms start moving into the copper, that any original zinc atoms that were distributed are uniform in their concentration throughout distance x. Okay, so we're already relying on a nice, homogeneous, uniform distribution of copper and zinc if zinc has previously been applied to our penny. Okay. Now, once we start the clock, so time is now building, and we're starting to evolve our concentration profiles. So at T greater than 0, the concentration of the diffusing species starts at a concentration value of CS, which is a surface concentration. and that is reflected by the numbers at x equals 0. Okay, so we see that all of these concentration profiles are anchored at that CS value. Okay, and they kind of decline from there as we go deeper into the copper penny. And then as we move to increasing x values towards x equals infinity, the concentration of the diffusing species, so this might be the zinc on the surface, which was anchored at CS at x equals 0, but the concentration of the diffusing species is now moving all the way down to approach the value that we have as our baseline C0 value. Okay, so that is, we will move asymptotically towards the concentration of zinc that we started with, and we don't change C0 at the outermost bottom boundary, which is represented by x equals infinity. Okay, so it goes therefore that the penny has to be very thick, and the zinc content at the other side is going to remain the same, reflected by the value CS, which is the other anchoring position for our concentration gradients. Okay, so all that to say, those are speaking to the boundary conditions that allowed for one solution to this second derivative, partial derivative approach for solving Fick's second law. Okay, so what does that solution look like? So we're kind of jumping to the punchline here, and we're going to see that the concentration of the diffusing species, represented by this concentration of that species, which is dependent on x and dependent on time. So this is our new zinc applied to the penny. The concentration of that minus the initial concentration of zinc that we may have had. Okay, so I'll just write initial here. That is our numerator for the left-hand side. Or the denominator for the left-hand side is just the difference between the surface concentration of zinc and the baseline zinc concentration or initial concentration that we had. Okay, we see that again in common from numerator to denominator there. Okay, so the left-hand side isn't too bad. We're, of course, very interested in that term there. That is sort of unknown. What is the concentration of the new diffusion species as a function of depth and time for my material? That first half of the numerator is usually what we're interested in. What's on the right-hand side? This is where we get the solution by partial derivatives. And we have now a complex mathematical application here called the error function. So this error function is a Gaussian error function. And you can see here, if you just simply Google it, that it has a interesting shape here. So here's applying, x versus y, and y is, of course, equal to the error function of x. And so it applies a complex kind of algorithm there. And you can see the end output of that is to give us a curve that you would agree with me, hopefully, looks a lot like our concentration profiles that we opened with. Notice that these are not linear and there's some curvature all the way through, and so this is one possible solution per the conditions we mentioned on the previous slide. Okay, so this error function is not necessarily something you can quickly kind of work with linear algebra methods. You're going to need more capable computing or advanced calculators for this. And so we'll see that we're going to apply a tabulated set of solutions for this to help us. Okay, so we'll just sort of leave that there for a moment and dive deeper into the elements within that error function. So what gets applied to the error function? So here's where we see some of the features that we've seen before. We now have the depth of interest, x. Okay, so if x equals 0, we're at the topmost surface. If we go to x equals infinity, we get to the bottommost surface of our penny. And as we go to values in between, we're now getting a depth, a specific depth into the penny, and we're going to use that to to understand what concentration of zinc might exist in there. Okay. So let me just write new zinc there again, as we've seen before. Okay, and the denominator of that feature, that argument that gets applied, that the error function does some work on, now has that diffusion constant that we've seen before, and it has time built into it. Okay, so we're going to take the product there, take the square root of the product of time and the diffusion constant, double that, that's our denominator, to a numerator that is our depth, and our error function does work on all of that. That gets a negative sign, and that gets added against 1 to equate to the left-hand side. Okay. So what does all that look like? So here's a table from your textbook, table 5.1. It is, if you want the x-coordinates of this data, okay, so it's giving us the x-coordinates for this red curve. And then we're getting the y-coordinates for the result of applying the error function per the z that's listed here. Okay. So what we see here is that z, or as I said a moment ago in my Canadian accent, z is represented by the pieces in our parentheses. Okay, so we're going to take the depth divided by 2 times the all root of d times time, and all of that represents z. So if we can calculate that, we would then turn to this table and look for the z value, and then provided we find it, we can simply read off the error function, and then that would give us the larger piece here. Okay, so this is kind of a process that's highly dependent on the precision of our table, and we hope to find the exact value for that. When we don't, we have some additional work to do, as we'll see in a moment. Okay, so hopefully that part looks straightforward to you. We should be able to easily get this larger piece, and then we can simply take the negative of that and add it against 1 to get the right-hand side calculated. Okay, so what about the cases where we don't find the exact value of z here? What can we do? Well, perhaps if we look kind of in here, we could say, well, imagine we were interested in 0.005. This is halfway along the first data. So by linear interpolation, we would expect the error function to be halfway along exactly. Okay, so that's going to be about 0.00565, if I've done that right. Okay, so that would rely on a linear interpolation. If we are halfway along between the two lines, we are going to be halfway along between those two lines in our answer. If we are a quarter of a way along between the first two to give 0.25 instead, we are going to be 25% along the first line to the second line. So we would take the difference between this, multiply by 0.25, and then add to where we started, in this case 0, 0, 0, and get to the linear interpolation between these two data points. Okay, so we'll do an example in a moment, but that's the main idea, is to use linear interpolation to get us to data that is not shown. So it's sort of getting pixels of data in this graph that may not be shown, and we assume that there's linear interpolation between the two, and that's going to be very close to the actual answer. Okay, so here's an exercise where you could see if you can follow this. So I invite you to maybe pause the video and see if you can do this. So try to find z if you know that the outcome of applying the error function value is this value here, 0.1825. Okay, so we're going to look for 0.1825. try to find Z. So clearly 0.1825 isn't going to be found in our chart, and we have to use the information provided on what the answer was to determine that. Okay, so 0.1825 is the outcome for the error function. Okay, so 0.1825, 8125, you can see here is somewhere in between here. And so here's where you might pause on this moment in the video and see if you can determine the Z for a value that gave us an error function of Z of 0.1825, and then resume when you've had a chance to get that. Okay, so kind of zooming in on that table, we have this little miniature of it. Clearly our outcome for 0.8125 is in between those two boundaries that we highlighted a moment ago. And so the question is, how far along is it between the two? And that's going to predict how far along our Z that is appropriate for that value would be. Okay, so in other words, we need to take the 0.1825 value minus the start point. Okay, so that's giving us, how far along between here and here. Imagine that's a ruler, how far along we are. So that's our numerator. And then we're going to divide that through by the total distance, so the limits between those two entries in our table. So that's going to be 0.8209 as our upper limit minus the lower limit, 0.769. And so that outcome here should be 0.8125 minus 0.7969, a numerator of 0.0156. And we're going to divide that through by the difference between the limits of our entries in the table, 0.8209 minus 0.7969, divided through by 0.024. Again, numerator should always be smaller than the denominator. Looks good. And the outcome there equals 0.65. So it looks like the value of 0.8125 is about 65% along the way to the next entry. So that means that our Z value is 65% along the way between 0.9 and 0.95. So that's the logic of the left-hand side here, which is to say the two are going to be equal. Okay, so here we got to solve for Z, and in doing that with the same idea, the limits 0.9, 0.95, we see them in the bottom, non-negative entries down there, and the Z value minus where we start at 0.90 is going to be our end outcome. Okay, so there our value is 0.93, and so it kind of makes sense to me. We're at 3/100ths larger than where we started, and that our upper limit is 5/100ths, and so 3 divided by 5 is 60%, and we're missing just the second, the 65%, given that we've had to answer back in two decimal points. Okay, so that is linear interpolation using table 5.1, and that would give us a Z value that we could use to do work on the inside if needed. Okay, so what I've circled there could be Z in a question.